this kind of problem we have done, but let's see. So, so we have a square, okay, 100 centimeter, side length is 100 centimeter. Okay. We are throwing, so in the square, we are scattering, so 51 points, okay, 51 points scattered, okay, inside. So we want to show that some set of 3 points can be covered by a square with side 20 centimeter. Okay, so show that some set of 3 points can be covered. So again, 3 points will be close enough in that sense, can be covered by a square of 20 centimeter. This could be given in a more interesting way, but so already we have a hint as to how we must partition the figure. Yeah, small boxes of 20 centimeters is the most obvious thing to do. So how many boxes are we going to get? 25. Okay, so just that's it. So you have 25 boxes. Okay, so these are not boxes, but anyways, doesn't matter. And so on. So then, so that's the first step. And then what can we say? Three points, right? At least 3 points will go in one box. Okay. So we partition in the obvious way, in the most natural way. And we have 25 parts. So 3 must go in one part, right? So 3 points must, at least 3 points rather, must go. Just writing a little bit so you can just, when you're writing, yeah, must go in some box. We don't know which box, and we don't know exactly how many points, but we know at least. So this was a very simple question, okay? Just a review. So let's just clear this. So there is a next question. Let's do that. Yeah. Yeah, this is a little different, okay? So it's, let's see, at least I was thinking, I don't have a clear solution. So this is problem 6 from the PHP chapter in challenges and thrills. That's a standard text also. Again, I said that in the beginning. Yep. So we are given 10 segments. We are given 10 line segments. Okay. With lengths. So the lengths are ranging from 2 centimeter to 54 centimeter. Okay. So you want to show that you can pick 3 segments from here, which will form the sides of some triangle, which can be made using which you can make a triangle. Okay. So can pick, that's what you have to show. Can pick 3 segments which form a triangle. So first basic question, if I give you any 3 segments of any length, do they necessarily form a triangle? Yeah. So we need to show that you can pick 3 segments. So you see the possible lengths that you have are restricted, and you have quite a few segments in that sense. And you need to show that you have enough to pick 3. So first you guys can give me some idea, then we can see. I will say no, because Pythagorean triplets are very, very special. Okay. So you may not be able to pick 3 Pythagorean triplets. Right. If that is what you want. Yeah. Yes, exactly. It may not be. So that's very, very special. So that may not happen. I so think I'm just thinking of this also and trying to generalize this also, which I'll ask you guys to try out later. So I will suggest just think freely. Don't have to think I have to apply Pigeonhole principle. Okay, just think freely. So one way in which I like to think sometimes is, I will try to avoid making a triangle. Yeah, that's all. Just try to avoid making a triangle and see, that may help you. Like, so if two numbers are there, and what numbers are not going to be there, certainly, and some things like that. Like, so just think. Yes, you have to use that. Okay, you have to use that, and in fact, you can think of it more specifically. Okay, like this: ABC form a triangle. I mean, if and only if it's if and only if, and so here I will say, and this slight adjustment can be very useful. You can have well, in our case, they are not all they're all unequal, but either ways, you see, this is they form a triangle. So we know that to form a triangle, some of two sides have to be bigger than the third side, and it has to be the same for all. But you can crisply put it like this. Now you may or may not use it. I'm just telling you this is useful. I've seen in many other questions, and so what I'm trying to say is a plus b is more than c. Yeah, you don't need the other two conditions actually. That's what I'm trying to say. If you order the side like this, basically I'm trying to say that the two smaller sides, their sum is bigger than the largest side. If you have that's it. You don't have to worry about the other two conditions. They will come naturally. Do you guys see the point? Huh? So maybe like if you take 2, 4, and 5, yeah, all you need to check is that these two are more than 5 because the other two are obviously going to hold, right? Okay. This can be very useful. So if you have not understood that, ask me. Otherwise, this you can use. So like you said, Naki, I need that any two sides, the sum has to be bigger than the third side, right? But if I take like I take this condition, I mean, like b plus c is bigger than a. I mean, this also you need in a triangle, right? Any two sides has to be bigger than the third side. But I am saying that you don't really need this condition. This will always be true for any three lengths like that, where a is less than equal to b less than equal to c. So once you order the vertices, you can forget the other two conditions. Like there are three conditions, right? Two sides at a time. But those other two conditions you don't need to think once you put an order like this. Okay, so let us try to think. If you think that the numbers are placed four, right? Yeah. So which portion should we look first? What I'm saying is, so if I pick three segments from a certain portion, I will certainly end up making a triangle. What is going to be that portion? So for example, if you think from 27 onwards, this portion is very special. Let's see. What if you pick three numbers from this portion? Yes. You see, so I am trying to avoid making a triangle, right? So I'm picking the segment from which I cannot, I'm picking this interval from which I cannot pick too many segments. Do you guys see the point? Right. Okay. I'm picking this interval from which I cannot pick too many segments because this is a very interesting interval. Yeah. Two of them will obviously become, yeah. So that's why that's how you have to partition your set. Like we were partitioning a geometric figure, but yeah, you can think of it in any way. It's not, but this is the way I thought. So from here, I can pick at most two. That's good for us, right? Already this huge chunk is gone and we cannot pick more than two. Okay. So we can maybe show in the end that, okay, if you want to avoid a triangle, you cannot pick more than 8 or more than 9, something like that. So 10 would imply you. Yeah. But anyways, so at most two. Now you guys think, how should you proceed? So uh, just giving so you guys can think, because that is really important here. To actively, aggressively think. So there are other intervals like this. Okay. Or you can even think that now you have a smaller problem. Now you have 8 segments and the numbers are from 2 to 26. You can think like that also. So I went from 54 to half of 54, right? So that if you obviously if you pick 3, then it will not work, right? Because two numbers which you have, they are more than or equal to half. So their sum would be more than 50. So it would dominate any third number. So now also you have to do something, you have to do the same thing for the rest of the interval, for the rest of the initial part. Huh. So does everybody see that? Yeah, maybe some of you are already also trying to say that, means thinking in that line. Okay. So now you know how to proceed. Okay, now there is the same thing. So you can either, because this is how I thought in the beginning, okay, because I don't know how to make the pigeons or whatever, right? I don't know how to make the cages. So I was just thinking, I don't know what exactly I was thinking, but I was trying to just, okay, like end part, I cannot. So I'm trying to avoid making a triangle. So in that portion, I will end up making a triangle. So I will only pick two to avoid making a triangle and so on. So then now that I know, I can, while saying this to you guys, I was thinking just on the bus, something like that. But now I can make it precise, right? In the sense that now I can say that you partition your set like this, okay? And then you can say to it, because now I know, so now I can say it in a professional way, as if, so like now you can say you have 6, and so what is happening here? Sorry. Point is that 12 to 6, and then 12 to 7 maybe. No, even 6 is fine, right? Yeah, so 6 is fine. 6 can be there. So so if you just divide it something like this, whatever. 1, 2, 3, 4, 5. No, so that is okay, right? Yeah, from 5 to 1, you can just keep it like that, maybe. Yeah. So you can just say, okay, look, now I've divided this thing into this, and from each you can pick at most 2. You can check by hand that maybe, no, but that is not true, right? From these you can pick 3 actually. So then what is going wrong? 1 is not there. Yes, that is important. Yeah. So 2, 3, 4, 5, and from here, is it true that you cannot pick 3? Yes, it is true. You cannot pick 3. You can pick at most 2. Yeah. So then it's so I mean, our solution would be like you partition the set like this, and you could say these are your cages and your pigeons are your numbers, and you are going to throw them. So you're going to throw 10 numbers. So if you're going to throw 10 numbers, then yeah, at least one of them will get 3, because there are only 4 boxes. Okay, that is the idea. Or I would say it like this basically. Yeah, this can have at most 2, at most 2, at most 2. Just check this last one, just check it. Maybe this can have 3. Okay, no, but not 4. No, but it cannot have 3. Yeah, it cannot have 3. So yeah, it's done. Good. Okay, so I was just thinking of a generalization, and so any queries with this? Okay, so just see, but I was thinking of a generalization, and you guys could try this. Okay? maybe I can put it like this. So if the lengths are given from 2 to n, now I could even put 1, I suppose. I suppose you could put 1, right? But either way, yeah, I think I just put 1 for simplicity. Yeah, 1 to n. From 1 to n. So we have segments from 1 to n. My point is, for this general numbers from 1 to n, now 10 will not be given to you, right? The question will be, I mean, how many line segments do I need to pick? Do I need to allow you to pick so that a triangle will be ensured? Yeah. So, you have these n segments and different choices of lengths, and you want to make a triangle, but you have sent someone to, buy some 10 segments, let's say. Right? So let's say, so someone is going to buy segments for you, but they don't know anything about triangles. Well, everybody knows this thing, but in the sense that they don't have it, let's say they don't know. Okay. Or let's say you are just closing your eyes and picking, right? So how many do you need to pick to ensure that even if you just, pick badly and so on, you will end up with a triangle? And the answer in this case was 10, right? So you don't know anything still. If pick enough, if you take enough samples, you will get the thing. Somehow you get some. It's a very interesting thing, right? So, but now you have to decide. Okay, you have to use that intuition. You have to use that extra math knowledge to make up for, let's say, if someone doesn't know anything about triangles, right? So 1 to n. So how many segments to pick at minimum, okay, to ensure a triangle? Okay, now you have to decide that answer is not 10, obviously. In this case, it will depend on n. Okay, so if I have numbers from let's say length segments from 1 to n, how many should I pick? The answer will come in terms of n. Okay, to ensure a triangle. If you cannot do this, answer it for 100 or something. Yeah, but I would ask others to think, because there's a clear pattern going on here, half, half, half. So you know that given n numbers, how many cages you are able to form, and then you would just say pick if there are k cages that you are making, you can say that you pick 2k plus 1 segments and come. Yeah, so you do the extra math and you make up for the naiveness there. Okay, so you can note this down. These are the harder variants, in the sense these are the other types of questions where they will ask you, what's the minimum number I need to do to ensure that 2 points are close enough, or this happens, or 2 consecutive something. Okay. Yeah. So note this down if you want to. Then I'll clear this. So when you're ready, I'll clear this. Okay, so then let's clear it. So here is this new question which I have not thought about. So this is problem 8 from Challenges and Thrills. So now we have 9. So Unab has given me these questions and he has not turned up today. It's very strange. So and there will be 9 lattice points. Okay. So, but now, so this one I don't know. So I don't know if you guys know, but I don't think everybody here knows 3D geometry, right? 3D Euclidean. Okay, so the question first, let me read the question. So there are 9 lattice points. So lattice points means points with integer coordinates. Okay. But let me just read it. Show that there is a lattice point in the interior of one of the line segments joining 2 of these 9 points. Okay, so then let me just simplify this question. So first the setup first is that you are in 2-dimensional space. Okay, forget about 3-dimensional space. when you, if you can do it for two-dimensional space, you'll be able to do it for three-dimensional space. The argument is same, but yeah. So the point is that in this plane, we are going to give coordinates to every point. Okay, so it's just natural. So for example, this point, 4, 1, right? 4, 1. So are all of you familiar with this? Oh, then it's perfect. Very good. Okay. So then this is 4, 4, so on. Okay. So 9 will be too much here, but let's keep 9 only because I don't know what the actual answer will be. How many will I need? So let's say nine lattice points are given to you. Okay. So we don't know what points are, but there's some 9 lattice points. So I'm drawing all the lattice points, but some 9 will be picked and given to you. Maybe this, I don't know, this, and so on. Some 9 points will be given to you. So what we need to show 9 lattice points, okay? Random. Okay? What we want to show is that, so you're going to join the lattice points that are given to you by lines. Let's say you join them by lines. Okay. And you're going to join all of them, and others are given to join them also, and so on. So you have to join all of them, right? So you have to join this, for example, this with this also. Okay. Anyways, so that's what you do. So you have to show that there exists, okay, two lattice points in this 9. Show there exists 2 among the 9, okay, which has a lattice point in the interior of the segment. Segment AB. So there exists 2, say A and B, okay, among the 9, such that when you join that line segment, obviously the endpoints are lattice, but their interior, there will be some point in the interior whose both coordinates are again going to be integers. Like in this case, you see this pink one and this pink one, right? Then when I joined them, you see their interior has a point. This point will be there in the interior, right? This point is not among those 9 points, but it is in the interior of this segment, which is formed from the 9 points. And that certainly is it. You can see that's a midpoint and it's integer. It's the lattice point. Okay, so that's the kind of thing we have to show. Okay. If the question is not clear, you can ask. Yeah. No. We only have 9 lattice points. The mark points are, the lattice points are obviously infinite because total lattice points are obviously always infinite because just integers, integer coordinates. But we are given 9 and we have to show that there are 2 of them among the 9 such that when you join the segment, okay, then that segment will have a lattice point in the interior. That lattice point is not in these 9, but that is a lattice point. Okay. Like in this case, you can see this one. The lattice point lies on the line. Yeah. So there is some lattice point which will lie on the line segment of some pair, some 2 points among those 9 points. So I think 7 will be enough in this case in 2-dimensional space. In 3-dimensional, you need 9. But we can do with 9 here. It's fine. So these are the variations. There are many variations. Okay. And what to do? Think. There's no rush. Think. So any ideas? You could see in this case, it happened via midpoint, right? The midpoint ended up, right? So in that case also, you have to show that if you take like A1, B1, A2, B2, and so on, A3, B3, and 9. So you have 9 points. So you basically want to show that there are 2 points whose midpoint also is integer. So there are 2 points in this. I mean, I don't know which 2. So that's why I'm writing it like this. There are 2 points such that their midpoint, this is the x coordinate of the midpoint, and also this. So both you want this and this to again be integers. There are 2 such points like this. Okay, that's what you want. I mean, that is not what is being asked exactly, but it will be enough if you can do this. And this is a good thing to guess, right? Because it should happen via midpoints, not some very strange thing. It's an easy question. Okay. So see, you can do it. So you see, you want this to be an integer. You want this to be an integer, and you want this to also be an integer. So that basically just means that you want AI plus AJ to be even. Yeah, and you want bi plus bj also to be even. So that's what you want. But how will you guarantee that? So it's like there are 9 numbers. So it's just break the problem up, right? There are 9 numbers, A1 to A9. Forget about the B's. You want to show that there are 2 of them you can pick whose sum is even. First thing, that's clear. But then the corresponding B's sum should also be even.
So we'll have even, 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 odd, even, and odd, odd. From a B. So we need at least two.
Uh-huh. Yes. Yes, yes, right. So basically, yeah. So let me write what you've said. So the pairs, the possible pairs are what? Odd, odd, which is good for us. Well, it's one thing by its own is not good or bad, but yeah, let me just write everything. Odd, even. Yeah. And let's write everything. Just write E and O, but so you see, these are the possibilities. Okay. And then
You need at least two of each.
not each, but you need at least 2 to be of the same kind.
Yeah, two. Yeah, sorry, two to the
Yeah. Does everybody see that? Yeah. No. But you're not going to add this and this, right? Think. Yeah. So what is going to happen is, so let's take an example. So let's take even odd example only. So the point is that you're not going to add this coordinate and this. So if there is some even odd, let's say some even and some odd, and let's take some other even odd. These two together are good. Do you see? Because when you add this two, it's even. And when you add this two, it's even. That is what you want. You see, because the midpoint, this point's midpoint of these 2 points is going to be an integer. Okay. So whenever you have 2 points of the same type of any of these 4, right? 2 points of the same type among these 4 types, then that's good. Then those 2 points come midpoint is going to be a lattice point. Okay. So now what should we do?
We need at least 5 points.
Yeah, we don't actually need 9 points. You see, if you have just 5 points, yeah, so this 9 can actually be confusing in that sense. If you just have 5 points, then 2 of them will be in the same place. 2 of them maybe will be of the same type, and that's it. Yeah, you can do this in a more one-dimensional way, at 2 steps, but that it's up to you. You have to think. I'll just give a different version of this, and you can think there if you want to. Okay, fine. So obviously, yeah. Okay, so the if this is clear, if not clear, then you ask me. So if this is clear, then I'll just make a very small variation. Okay, nothing fancy, small variation, but not of the same type, as to some three-dimensional. No, in two-dimensional space only we can make. Let's say that there are. I don't know how many you will need, but just for safety, let me. No, wait, I know how many you'll need. Just give me a second. Seven, yeah, seven are enough, but let's just keep 9 only. Okay, 9, let's keep the same. Yeah. 9 at show that there are 3. Okay, show that there is a triangle whose centroid. So the centroid coordinates is the average of 3 points of the vertex. Okay, so you can assume that if you have not seen the proof, show that there is a triangle. There is a triangle with vertices in this with a lattice point in the interior. That's all. Yeah, so till now I was just asked, the question was just that you have to find a line segment. You have to show that there are 2 points whose line segment contains, but now I want to show there are 3 points whose interior has a lattice point. Now that interior lattice point again is not among these necessarily, but it's a lattice point. Okay, just think about it. This is a simple problem. Yeah, I think let's stop today. Okay, let's not do too much. So yeah, stop here today. But let me see, maybe I can show you the book Brualdi. I suppose some of you would already have it. But okay, Challenges and Thrills is good, but I always found Brualdi is because he is a combinatorialist, real one, like top class, like first class combinatorialist. Okay, so if you read him, then it's useful now and later, and just different from Challenges and Thrills. The quality is just different. In problems, anybody can. I can also give you problems, but Brualdi is a combinatorialist. So I'll just open the book and show, and also just show the problems in front, which you can just try. Then we'll stop. Okay. Let me just do that. And you can, even the book has an Indian edition, so you can easily buy. Even if it's Western edition, you can buy. But it's Indian edition, so shouldn't hesitate to buy it. Or PDF, it's obviously there, but always good to use a book. So in this book, you can see this is just it has everything in basic combinatorics. Well, yeah. But yeah, so we are looking at Pigeonhole principle. Okay. So the problem with this book is very theoretical. So it goes into a lot of theory. Wait, so you guys cannot see the screen. Yeah, because it changed. See, so we go to the beginning. So this is the book. Okay, you can see this is the book. It's a wonderful book, and Pigeonhole principle. Every line is worth reading in this book. Okay, but it's a little theoretical. It doesn't have Olympiads as a center of focus. But don't let that think that it's not useful for entrances and Olympiad. It's very, very good because it's solid. There's a lot of things, but we will see some of them later. But yeah, the exercises are really beautiful. Okay, so I'm not giving you the first 3 because you have to read applications to go back and read. You should read the chapter if you have time, but my first priority will be that you do these problems. Okay, so obviously you see 4 and 5 are simple, you can try. 7 is good enough, you can try, I suppose. 8 we have already discussed, but you can try. 9 is good, you can try. 10 is good, you can try. Yeah, 11, no. No, so 11 is a little difficult, but you can try. But till 10, you try. Okay, 11, I don't know if you can do it. Good if you can do, but it's a little difficult. After that, I'm not telling you to try. You can try, but because this requires some theory, so not going into that. But yeah, till 10, I will say you try. Apart from the generalization, you can go back and read this there, but yeah, application and then do. But so this you should try. Okay, that's a concrete homework. And as I've said, there is other challenges and thrills that you look. Arthur Angel, I'm not giving now. Later you can see. If you have time, you can see. Okay, so that's it for today. We will meet on Monday. So today we didn't do any like we solve problems, but Monday I plan to do two theorems. Two theorems using Pigeonhole principal idea, which are number theory. Okay, will good tools to solve very interesting number theory questions and also learn some really fundamental things about numbers and set solutions to integers, which are standard tools by themselves. That's the goal of Monday, two things, and then we'll try to solve these. Okay. So that's it for today. Thank you. Bye. Good.